Lesson 3, Modeling Periodic Behavior. So consider the following graph. So you're given a graph here of a particular pattern. And so what is unique about this graph? Well, if you notice what's happening with this graph, it has a pattern that repeats itself at regular intervals. So that's what's unique about it. It has a pattern that repeats itself at regular intervals. And depending on how you see the pattern, you might have seen it as the spike happening first, and then a small bump, and then a larger bump. Okay, so one way of looking at that pattern is that there's a spike, and then a small bump, and then a bigger bump. Or you may have seen the pattern differently, and you might have seen it as a small bump, a big bump, and then a spike. So a small bump, a big bump, and then a spike. Or maybe you saw the pattern that's repeating itself as a big bump, a spike, and then a small bump. So depending on how you saw the pattern, one of those three patterns are repeating itself at regular intervals. Okay, and what we're going to be looking at are some special features about periodic graphs and periodic behavior as well. Okay, so let's take a look at what a periodic function looks like. So a periodic function is a function whose y values have a pattern which repeats itself at regular intervals. So for example, if you look at this graph, if I follow it as a large bump, a spike, and then a small bump, what you'll notice is that every 3 units, the pattern seems to be repeating itself. Okay, every 3 units, you'll notice that the pattern seems to be repeating itself. Okay, so what you'll notice here is that's the horizontal length of one of the cycles. Okay, so it's about 3 units long. So from 0 to 3, I get the large bump, the spike, and then the small bump as well. Okay, and if I go back here from -3 to 0, I have the large bump, the spike, and then the small bump as well. Okay, so that's what's special about a periodic function. So what that means is in the cycle, every 3 units, the pattern should repeat itself. Or in other words, every 3 units I should land back at the exact same point that I was previously. So for example, if I'm at this point in the cycle, then that means 3 units later I should be at the exact same point again. So if I go ahead 3 units, 1, 2, 3 units, you'll notice that I'm at the exact same point again. And if I do that again, if I go ahead 1, 2, 3 units, I'll be at the exact same point again. And so it doesn't matter where in the cycle you're looking, but because it takes 3 units for one cycle to be completed, it doesn't matter which point you choose. 3 units later, you'll be back at the same place again. So let's say I chose this point on this particular cycle of the pattern. 3 units later, I'll be in another cycle of the same pattern, and I'll be at the exact same point. So 1, 2, 3 units later, I'm at the exact same value of y. 1, 2, 3 units later, I'm at the exact same value of y. So it takes 3 units for the pattern to repeat itself and for you to actually end up in the same place that you were in one of the previous cycles. Okay, so that's just a little introduction to periodic functions. So some of the special properties of periodic functions include some key words here. The first one is a cycle. A cycle looks at one complete pattern. So for example, the pattern that we were looking at earlier is a big bump, a spike, and then a small bump. So that's an example of one complete pattern. The period of the function looks at the horizontal length of one cycle. So how long it takes for one of those cycles to happen. So you want to know, or we want to know what the horizontal length of one cycle is like this. So we want to know what this is. Okay, that represents the period. One way to calculate the period is to take the higher x value and subtract the lower x value from it. So let's say this was at 0 and this is at 3. Then you would just subtract 3 and 0 to get the period of the function, which is equal to 3. And we saw that earlier in this graph as well. Okay, so if I looked at the cycle here, so from 0 to 3 is the horizontal length of one cycle, so I know that the period of the function would be 3. Okay, and then finally, amplitude is the other key word, and what the amplitude represents is half the length between the maximum and minimum values. So we can look back at this graph to try to figure out what the amplitude is. So we're going to look at half the length between the maximum and minimum y values of a periodic function. So in other words, we're looking at half the height. Okay. So for example, if I'm trying to find the amplitude of this graph, what I would look at is the highest y value and the lowest y value, and I'm going to look at half of that length. Okay. And so there's a little formula here that you can use, and what the formula looks like is y max minus y min, so that'll give you the height of the graph, and half that height would mean you're just going to divide it by 2, and that'll give you the amplitude. Now because amplitude looks at the height, half the length or half the height of the graph, it's always going to be a positive number, so keep that in mind. When you are looking at amplitude, it's always a positive number. So for this example here, if I go back to try to calculate the period and the amplitude, the period of this graph we already talked about is 3. That's how long it takes for one cycle. And the amplitude, if I try to calculate it, my maximum y value is 7 minus, my minimum y value is 0, and if I look at half that height, so that would tell me that the height of the graph is 7 units. If I look at half of that, I get an amplitude of 3.5 units. So half the height would be about 3.5 units. Okay, so that's what, those are some special properties of periodic graphs. Okay, solving with periodic functions. So sometimes you may be asked to solve for the value of the function at a particular value of x, and so you can actually use the period of the function to extrapolate. So for example, if I'm trying to figure out, okay, if x is equal to 1, what's the value of the function? Well, that's easy because x equal to 1 is actually on my graph, and I just go up to what the value of the function is to figure out what the value of the function would be at x equal to 1. But the problem sometimes becomes when you're looking for a value of the function when x is a number that's beyond the range of your graph, and so you could use the period of the function to help you extrapolate those values. So since the y values of a periodic function repeat every p units, what you can do is add or subtract a multiple of p to help you do the extrapolation. So for this example here, it asks us to use the graph above to determine the value of the function at the given values of x. So in this case, we're looking at the value of the function when x is equal to 10. So this is function notation. And what you'll notice is that x equal to 10 is somewhere over here. Okay, so our graph goes up to about 6 units, but we're looking for a value of the function at about x equal to 10. Now, because the function repeats itself every 3 units, what I can do is sort of backtrack a couple of cycles so that I'm at a point inside the graph. So what I'm going to do is I'm going to simplify the brackets here, and instead of looking at x equal to 10, what I'm going to do is backtrack a couple of cycles so that I'm within the range of my graph. So because the function repeats every 3 units, so remember that the period of this function is 3, what I can do is subtract 3 units so that I can sort of come back. Okay? Now if I subtract 3 units from 10, which is subtracting 1 cycle of the graph, what that ends up doing is giving me a value of x which is equal to 7. Now that's not enough because 7 is still beyond the range. So maybe I can subtract another cycle of the graph, and that'll give me an answer 4, which is within the range of the graph. So what this will give me is f at 4. So what this means is the value of the function at x equals 10 is the same as the value of the function when x is equal to 4. And that's true because this is just 2 cycles behind the one that we're trying to actually look at. And then from here it's pretty easy because you have a graph. All you need to do is go to x equal to 4 and try to find the value of the function. And so the value of the function would be 1. Okay, let's try that again with a different value of x. So this time we have x equal to negative 16. Negative 16 is way over to the left. And so what that means is we need to increase and move up through the cycle so that we're within the graph again. So this time instead of decreasing to get within the graph, now I'm going to increase so that I'm within the graph. And you only really, like I said, need to add or subtract a multiple of p. So here what I could have done is f of 10 minus 6. So that's still a multiple of the period of the function, and that would have just saved a little bit of time for me. This time, because I want to get within the range, I'm going to take the value of x that I have and I'm going to increase it by a multiple of the period. So the period is 3. If I add a multiple of the period like 15, that'll give me an x value of 1, or -1, sorry. And x equal to -1 is within the range of my graph, so all I need to do now is find the value of the function when x is equal to -1. So I go to the left -1 and I plot the point, and the value of the function when x is equal to -1 is equal to 4. Okay, so in case you're still wondering how I got 15 here, this is just a multiple of 3, which is a period of the function, and what this means is this is 5 cycles ahead of where I'm actually trying to find the x value. So x equal to -16 is somewhere over here, so I have to move up 1, 2, 3, 4, 5 cycles before I actually got within the range of the graph. Okay, so that's how I got that value. Okay, we're going to look at a slightly different example, and we're going to try to identify whether or not the graphs that we have here are periodic. If they are, we're going to state the period and the amplitude. If they're not, then you can't state the period and the amplitude. Okay, so you can only state the period and the amplitude of periodic functions. So for each of the following graphs, state whether or not it is a periodic function. If it is periodic, then determine the period and the amplitude. So starting with the first graph, what we're trying to see is whether or not the pattern repeats itself at regular intervals. So what that means is, if I take a portion of the graph and I lift it and I shift it over the same number of units, it should repeat itself. And in this case, it looks like it may be periodic. However, it's actually not periodic because I know one cycle sort of looks like it's this amount here. So it looks like it's at the minimum hitting the maximum and then going back to the minimum. But as you move across, that horizontal distance is actually increasing. It's getting wider and wider and wider away from each other. So if you compare this here to this here, it's much different. And if you continue here, this part of the graph, if I keep trying to overlap it, doesn't actually overlap here. So this is actually not periodic, which means I can't state the period and I can't state the amplitude. Okay, let's take a look at the next one. Is this one periodic? Yes, it is. And I know this is periodic because if I take a small portion of the graph, so let's say I look at this small portion here, there's one cycle of the graph. If I take this orange piece here and I lift it and I shift it to the right, or if I shift it to the left, it'll keep repeating itself over the same number of units. Okay, so this little curve min to max back to the min, if I lift it and I keep shifting it over, it'll overlap with the entire graph. So that's one cycle of the graph. Now in order to state the period, I need to know what the horizontal length of this is. So this is going from -6 to -3, so I know that the period of the function is 3 units. And then the amplitude, if I look at the maximum and the minimum, half that distance is actually what the amplitude would be. So my maximum here is 2, my minimum here is 0. Half of 2 minus 0 gives me a height of 2 units, and half of that is equal to 1. So the amplitude is equal to 1. Or you can use the formula for amplitude. The maximum y value here is 2, minus the minimum y value here is 0, divided by 2 gives you 1.